So I'm really excited to share some of our recent work on developing an integrative framework for learning dynamical systems from data. So I hope it's not a controversial statement that the brain is a complex and nonlinear dynamical system, and the neural state is constantly evolving over time. This perspective of looking at the temporal evolution of the neural state has been really insightful for explaining a wide array of cognitive behaviors. And as such, numerous approaches have been developed to learn these dynamics directly from data. However, a lot of these approaches are still typically applied to single sessions. So we would train these modules from scratch on each recording session. Now, in parallel, foundation modules have led to significant breakthroughs in machine learning. As we have seen over the past 2 days, they have been really successfully applied in neuroscience as well. And foundation modules are really cool because they are much more data efficient on downstream tests. So we can pre-train this large module and then fine-tune it on fewer samples on downstream tasks. They can also generalize to a wide range of downstream tasks. And it also alleviates a lot of the challenges that come with training these large modules from scratch. So we wanted to see if we can take a similar integrative approach, but for learning dynamical systems from data. Now, when we talk about foundation models for neuroscience, and as we've also seen over the course of the workshop, we can think of them in terms of different possible architectures. So, of course, transformers are widely popular for developing foundation modules. We also have this class of linear state space modules, such as S4, S5, and Nanda. There is this other class of architectures, which are nonlinear state space modules. And these are not really explored in the space of foundation modules as much. But we like nonlinear state space modules because they can capture a really rich repertoire of dynamical behaviors. And it also, like picking between these different architectures also kind of depends on what applications we might be interested in. So there's been a lot of talk on engineering applications, and architectures like transformers and linear SSMs are really good candidates for these applications, but nonlinear state space modules, I believe, would be really crucial if we're interested in quote-unquote understanding neural computation through this perspective of dynamical systems. And they could also be useful for some engineering applications. For instance, if you want to do online estimation of the neural dynamics, for instance, in closed-loop experimental paradigms, or for designing some perturbation approaches. And what these nonlinear state space modules allow us to do is have a module of the underlying dynamics from neural activity. So let's say we have some data from a subject performing this reaching task that I'm plotting with this raster on the left. We can train a nonlinear SSM on this data and then use it to forecast the long-term behavior of the system, as well as predict the future neural activity. And this is kind of the downstream task that I will be focusing on for the rest of the talk. Now, of course, this is a foundation module workshop, and we care about like integrative approaches for nonlinear SSMs. So we would want like a Swiss knife nonlinear SSM module that is able to work across different sessions, animals, as well as potentially different cognitive tasks. So we kind of address this in our recent work with Mehdi and my collaborators, Hurwitz, Hyungju, and Matt. and our manuscript is going to appear in ICLR this year. I'm going to call it Foundation Module version 0.1. And you can check out our paper for technical details. Today, I'm just going to try to provide a more broader overview of our method. So just to make sure we're all on the same page, I'm going to circle back to this idea of studying neural computation through dynamics. I think this has been covered before, and I think we're all familiar with this manifold hypothesis, where high-dimensional neural activity tends to be confined to a much lower dimensional region in this entire in the state space of neural population activity. But the specific thing that you're interested in is modeling how the neural state evolves in this low-dimensional manifold. We can easily do this using like a nonlinear SSM module where we have Z of t, which defines our latent state. We have f theta, which is our nonlinear dynamics module, which tells us how the state evolves over time and defines this underlying flow field. And finally, we have the g-dot, or the likelihood function, which maps from the latent state back to the high-dimensional observations. Now, as we know, there are challenges with integrating really heterogeneous recordings, especially for learning these state space modules, because all brains are different. So the number and tuning properties of neurons that you record from are also quite diverse. Now, there have been some approaches for kind of bringing all of these heterogeneous recordings into a common space. And two of the popular ones are the unit ID approaches that have been used in the POYO modules, and the session stitching that has been used in LFADs, as David already talked about. And in order to deal with the differences in the number and tuning properties of neurons, we're going to take the session stitching approach of LFADs. But next, we also need to talk about sort of the diverse dynamical behaviors that we might expect across these recording sessions. So if we only had recording sessions during the same behavior, then there's been a lot of evidence, which Chetan talked about, and also Hee-Woon talked about yesterday, that we expect the latent dynamics to be the same when subjects are engaged in the same cognitive task. So based on this, we can assume that the dynamical system across these recordings is the same, or rely on similarity in the dynamics, and this has been successfully applied before. In parallel, there have also been works that look at recurrent neural network modules of the brain, and they try to capture the diversity of dynamical solutions that might underlie flexible behavior. And we sort of built on this approach, and we introduced a framework where we were able to learn a family of dynamical systems by integrating different recordings. And our approach is called Meta-dynamical state space modules. And just to give a quick overview, let's say this is the state space module corresponding to recording A on the left. Now, since we're interested in modeling the variations in the underlying dynamical system itself, we introduce a hierarchical variable, which I'm going to call the dynamical embedding. It's essentially a really low-dimensional vector. Now, through large-scale training, we can learn an entire space of these dynamical embeddings, such that a different point in the space, a different point in the space instantiates a different dynamical system which could capture topological or geometrical properties corresponding to Jakartan B, and also define the corresponding state space module. And now just jumping into what the generative module for these nonlinear SSMs might look like. I'm going to start with the single session generative module. So typically we use MLP or multi-layer perceptron to model how the latent state evolves from time t to time t plus 1. So we might have some hidden layers and non-linearities. This allows us to have really expressive dynamics while still having a lower dimensional latent state. And now, when talking about this hierarchical module for multiple recordings, we additionally introduce these embedding condition modifications to our MLP. So for each session, we have a hypernetwork that generates low-rank modifications to the weights of this MLP. So we have some shared components, and then we have some session-specific components corresponding to these low-rank updates. And for training, this is essentially an extension of a sequential variation of autoencoder. So we can train the module jointly by maximizing this objective, which is commonly called the elbow. Essentially what we're doing is we're learning how to deconstruct the observations given the latent state. We're learning the dynamical system for each recording session. And we additionally have a regularization on the embedding that kind of encourages it to be close to 0 or centered around 0. We applied our approach to motor cortex recordings. We specifically picked these two popular tests, the center out and the maze. So in the center out, the subjects are trained to use a manipulandum to make targeted reaches to one of 8 target locations. And on the maze, they directly control a cursor to move to a target location while avoiding obstacles. And we used 44 sessions for training that span different axes of variability while still having some shared components. So after training, we can sort of visualize what the module learns by looking at this low-dimensional embedding space. We do see some interesting structure emerge. So in green and yellow, I'm plotting the 2 subjects from the center-out task. And the blue points show the sessions from the maze task. And we see that it learns a somewhat coherent structure across the center-out task, which kind of makes sense because we have more data from that task. And we can also sort of verify that, so we can pick 2 sessions from corresponding to the 2 different tasks and see that it captures these non-trivial variations in the underlying dynamics. So I'm plotting the dynamical system trajectories that are generated from the module and the corresponding behavior predictions. So this is kind of what we would expect if we were to put separate modules for these data sets. This is just confirming that we can also do this in a unified space. Okay, so now that we have this module, we of course want to see if it's useful. So we test this by looking at generalization to new recordings. So we leave out some sessions from a subject that we've included during training. And we also use some sessions from a held out subject. And we see that the pre-trained module does provide a useful inductive bias for learning dynamics, especially in very low sample regimes relative to baselines. It was also really encouraging to see that the module does benefit from large-scale pre-training. So if you were to only use 4 sessions, which I'm plotting with the dotted lines, the module is not able to generalize as well to these new recordings, but then when it has more data, it's able to learn like some coherent structure that might exist across all these heterogeneous recordings and generalize much better to new data. So jumping to the takeaways, we introduced an integrative framework for learning the family of dynamical systems across session subjects and tasks. And the dynamical embedding space that the module learns effectively captures variations across these different recordings and provides a useful inductive bias in trial-limited regimes. So now that we have this module, we can also think of potential applications. Like I mentioned before, this can be really useful if you want to learn dynamical systems in closed-loop paradigms where we might not have a lot of data to effectively estimate the dynamics. Or it can also be potentially applied to look at naturalistic behaviors to the lens of dynamical systems, where again, we don't really have really structured trials or any trial repetitions. But more broadly, it can be also applied to investigate, for instance, learning-induced changes in neurodynamics and potentially study variability across subjects, as well as variations when the same subject is engaged in different context-dependent behaviors. So with that, I just want to thank my lab, especially Mehdi and my collaborators, Maj, Ryoo, and Hurwitz, as well as my funding sources. I also want to thank the organizers for putting together a really cool workshop, and thank all of you for your attention. Before moving on to questions, I do have one extra slide. So this is just the sea of potential NeuroFoundation modules. We've seen a lot of interesting ones over the past 2 days. I guess one strategy that we can use is exploiting all the architectures and training strategies that have worked for building LLMs. But I think it's also important to explore different architectures and modeling choices that might make more sense for neuroscience. And yeah, one year to do that is the symposium that's going to take place at Chimplimo in October, Neurocybernetics at Scale. I think it's going to be pretty interesting for a lot of people at the workshop. And it's being co-organized by Mehdi, who definitely did not tell me to advertise this. And yeah, with that, I'm happy to take questions.